me start sharing my screen. And I have to apologize, but the notes for today are sort of a little bit all over the place. Last class, we were working on the chapter 5 notes. And so all of the things that are course announcements are there at the top of chapter 5 notes. Chapter 4 homework was already done. It's graded. It should be correct in Blackboard. The chapter test 3 is on chapters 4 and 5. It'll be due by November 23rd. After next class, we'll talk about when it'll be available. It'll probably be available after class time on the 16th. Homework 5, we had said last time, was due on November 23rd. And so I am bribing you. I don't know if you remember, if you turn it in by the 16th, I'll give you, end of the day, the 16th, I'll give you 10 points extra credit solely so that I can turn around and grade it. And you can see how you did on the homework before you take the test. Now, before we do anything else, we had covered the first 2 pages of chapter 5 homework in class last week. And the 3rd page is on multiplication and division assigned numbers, which hopefully nobody was too scared of taking a quick look at that. Does anybody want to look at anything from any of the chapter 5 homework? Because I do have the virtual textbook ready to roll. Does anybody want me to open the book and look at any of the chapter 5 homework questions? I'm taking that as a no. So in which case, what I'd like to do next is go back to when we had started chapter 5. The night before we started it, we had looked at some of the chapter 5 activities, and we had looked at the activities for, defining sign numbers, adding and subtracting sign numbers, but we didn't get to that activity. Chapter 5 in the version of the activity manual that I was using over the summer when I was putting the course together. It was activity 5, multiplying and dividing sign numbers. I'm just going to check against yeah, it is still chapter 5, activity 5, multiplication and division patterns. Did everybody get my note asking you to have your activity manuals today? Because after we finish the content of chapter 5, I had thought that we would spend the rest of the evening just looking at chapter 6 activities, and you need some of those punch out manipulatives from the back. And again, while I'm on this roll, before I forget, I was telling Naomi before class, if next semester you're taking Math 109, it's a daytime class. It's not 3 hours, so hopefully that'll make it a little bit better on all of us. But also keep your textbook and your activity manual. Your textbook and your activity manual for Math 108 are the same material as you need for Math 109. Keep them, keep them, keep them. You will need them for Math 109. Math 108, we're covering chapters 1 through 7. Math 109, we're covering chapters 8 through 14. So make sure you hold on to those materials if you're taking Math 109, okay? Nothing breaks my heart more than when I've got start teaching Math 109 and people sold their book back to the bookstore and have to rebuy it. Don't. Keep your book because you're going to need it for next semester. Okay, so that activity, multiplication and division patterns. And so we want to explore patterns to help us develop rules for multiplication of integers, and inverse operations develop rules for division of integers. So it says that you're supposed to work individually. So In each of the following set of problems, complete the products you know, and then look for patterns to fill in the missing entries. And so let's look at 1 through 6. Did you folks want to work on these together? Or did you want me to give you a few minutes to try them on your own? I'm seeing people working, so I'll shut up for 5 minutes for you guys to try work on them on your own. Leanna, we're working on the activity 5 for chapter 5 from the activity manuals. So everybody's working on them kind of independently, and then we're going to go over. Okay. Can we go over the first three? As I went through, in number one, I noticed we were each time taking the numbers and multiplying them by 4. 4 times 3 was 12, times 2 was 8, times 1 was 4, times 0 is 0. And as I looked at those first entries, as you looked at this last column, what did you notice about them? As the second factor decreased by 1, didn't the product decrease by 4? And so as I make that second factor continue to decrease by 1, doesn't it make sense that the products would continue to decrease by 4? So I'd get 4 times negative 1 is negative 4, 4 times negative 2 is negative 8, and so on. And then looking at the other, if I had 4 groups of 5, I'd have 20. If I have 3 groups of 5, I'd have 15. If I had groups of 5, I had 10. And in the same way as this factor went down, the products also went down by 5. And so as I look at the end results, well, positive times positive is positive. But what would you say the rule would be for multiplying a positive number and a negative number? Any ideas? The product of a positive and a negative will be?
Negative.
Negative. Beautiful. And the product of a negative and a positive will also be negative. So we can generalize, can we generalize to say that if one factor is positive and the other is negative, the product is negative. And then, did you folks fill in the patterns for questions 4 and 5? 4, I'm taking negative 3 times 2. Negative 3 times 1 is negative 3. Negative 3 times 0 is 0. And this time when I'm taking this negative number and multiplying as the other factor decreases, the products increase. And so if I were to continue with that pattern, they would increase by 3 each time. And likewise, 3 times negative 6 is negative 18. 2 times negative 6 is negative 12. 1 times negative 6 is negative 6. 0 times negative 6 is 0. And again, while that column decreases, the other column is increasing by 6. And so to keep up with that pattern, this would be positive 6. Negative 2 times negative 6 would be positive 12. And negative 3 times negative 6 would be positive 18. And so what would you tell me about the product of 2 negative numbers?
Positive.
The product of 2 negative positive. And then to extrapolate from there and try to get the rules for division, we're going to make use of those number facts. So since 12 divided by 4 is 3, 12 divided by 4 is equal to 3 by definition, because 12 is equal to 3 times 4. In general, A divided by B equals C means that C times B equals A. So what would negative 12 divided by 4 be? Well, negative 12 is equal to 4 times, it would have to be negative 3. And so we'd say that negative 12 divided by 4 is negative 3. And using those fact families, we'll come up with our rules for division. So far, so good. If so, I think with the notes we left off at page 11, which was showing number line representations for subtraction of signed numbers, lining them up head to tail. And then for multiplication, I've got a blank sheet. So I'm going to go down here and add a blank page after. And so let's go through and let's look at integer multiplication and division. And so I think when we were looking at whole number multiplication, I think we said that we could look at multiplication as repeated addition. And so if I look at 4 times 3, I can look at that as adding 3 to itself 4 times to get 12. And so if I look at trying to, with manipulatives, show this relationship, I can look at, in a loop, we'd have 4 groups, each containing the counters for positive 3. And for each of you, would this visually represent that idea that 4 times 3 would equal 12? So far, so good? If so, we can also look at 4 times negative 3 to be the sum of 4 negative 3s. Oops, I lost a plus sign there, sorry. And so we can again look at having 4 groups, each containing the counters for negative 3. Those are supposed to be red, but we're showing them as hollow because I'm writing in black and white, I'm sorry. And so this would show us that 4 times negative 3 is equal to negative 12. And the first number told me again that I had 4 groups of the second number, negative 3. Instead, if I look at negative 4 times 3, because that's negative, I can look at that as the idea of taking away 4 groups of 3. And so I'm going to start with a representation for 0. And if you can remember, last class we said any representation would be equivalent to 0 if it had the same number of black counters as red. So every time I put in a black, I want to put in a red. And I'm going to keep doing this until I have enough black counters in there to be able to take -4 of those groups, or to take 4 of those groups of 3 out. And so since we're taking it out, it's like a -4 number of groups. And that would show me, once those are out, that my final result would be -12. So that would be one visual way of, like we did with number patterns on that starting activity, showing that -4 times 3 would be -12. And so lastly, if we want to show with counters -4 times -3, that first -4 means that we'll take away 4 groups of the counters for -3. And so we can think of that same starting with 0. So we're starting with 0, which would be the same number of black and red counters, the positive charges and the negative charges, so to speak. But this time, we want to take away 4 groups of -3. And so this time, on the other side, we'll be taking out 4 loops, each containing the representation for -3. And as we look at what's left, we get that our result for -4 times -3 is +12. Or that same idea of the product of 2 negatives is positive that we came up with when we were looking at our activity to start. And so, is everybody all right if I add a page? We'll get our rules for multiplication. And we'll say that if m and n are whole numbers, if we take m times the opposite of n, or m times -n, we'll get a negative product, -mn. Instead, if we take negative m times n, we'll also get the negative product mn. And if we take negative m times negative n, that product will give us the positive product m times n. And we show these with counters. We should probably also be able to show that multiplication of integers on number lines. Using the idea of repeated addition. And so if you remember, if on a number line I wanted to show 3 times 4, on my number line I'd start with 0. And I would add 3 arrows of 4. And again, that's a positive 4, so those would be arrows drawn to the right. And when I'm adding them, I draw them tail to head. So where one ends, the other starts. And so we would get that our product is what everybody would think it should be, positive 12. So far, so good. So then if I wanted to look at 3 times negative 4, I would add 3 groups or 3 arrows for negative 4. And so again, I'm going to start at 0. And I'm going to think of adding, which is again, drawing tail from head, arrows for negative 4. And again, remember those arrows, those negative arrows, are arrows that point to the left. So that's my first arrow of negative 4. I'll add to it my second arrow of negative 4. And then I'll add on that third arrow of negative 4. And this would verify that 3 times negative 4 would give me negative 12. Now, instead, if I were to take negative 3 times 4, because this is negative, instead of adding 3 groups, we're going to take away 3 groups or 3 arrows of positive 4. And so again, I'm going to start at 0. But if you remember correctly, when we took away, we started with the arrowhead and worked to the tail. We worked backwards. So that's 0, take away 1 group of 4. And they're positive 4s that we're taking away. So the arrows are pointing to the right, but because we're taking them away, we're going from the head to the tail. And so in that way, I would be showing that taking away 3 groups of 4 would give me negative 12. And so then lastly, to look at negative 3 times negative 4. Again, we're starting at 0, but this time we're taking away 3 of the arrows for negative 4. So the arrows for a negative number point to the left. I'm sorry, I'm trying to draw and talk at the same time and it's not working. Point to the left, and because we're taking them away, we're going to put that again, headed to tail. So here from this point, we'll put the head of our next arrow of negative 4. And at this point, we'll put our head of our next arrow at negative 4. And so when I take away those 3 groups of negative 4, I get negative 12. I apologize. No, I don't get negative 12. I just circled a positive 12. And then if you read through this last section of the chapter, they also use mail-time stories for the multiplication of integers. And so let's say, for example, the letter carrier delivers 5 bills, each of which you owe $20. Well, that would represent positive 5 because he's delivering it. And since it's a bill, it's negative 20. And so if the mailman comes with 5 bills and each of them is worth, you owe $20 on, you're out $100. However, instead, if the letter carrier takes away 2 bills where you owe $10, since he's taking them away, we'll look at that as negative 2 times negative 10. And so if he takes away that debt twice, it's to your advantage of $20. I think this last one's a little bit of a stretch. Usually the mailman doesn't take away your bills, but it's a way of explaining that idea that taking away debt, that double negative type of thing, would give you a positive result. And then Any questions on those before I carry on? I feel like I'm talking to a wall because I can't see you guys, and none of you are answering my questions. You're driving me crazy. So everything okay so far? Any questions?
No.
No questions? All right, then we're going to look at, I'm going to add another page for division. We're going to say that division is the inverse of multiplication. Or we're going to say that, like we had at in the activity, A divided by B equals C if and only if A is equal to B times C. And so M divided by negative N will give us the negative of M divided by N. Negative M divided by positive N will give us the negative of M divided by N. And negative divided by negative will give us a positive quotient. And putting all of these things together, we get a set of rules for multiplication, or actually rather than rules, let's call them properties. For the multiplication of integers. And so the first property we're going to concern ourselves with is that closure property. And so, can anybody remember what we meant by that closure property when we were looking at a set with, oops, that was not what I wanted to do. When we were looking at a set with an operation. If I look at the multiplication of two integers, can anybody remember what it meant for a set to be closed under the operation? Remember, if a set's closed under the operation, it means that the answer is always an element of the set. So integers will be closed under multiplication because we'll say that the product of two integers is always an integer. And so they're closed. When I multiply two integers, my result is an integer. The next is that commutative property. Of multiplication. And if we go back and look at the examples that we did, both with the counters and with the number line, I think we showed that for any two integers, m and n, m times n is equal to n times n. Likewise, we'll show that the associative property of multiplication holds for integers. So we could say that m times n times some other integer p is equal to m times n times p. We'll see that multiplication distributes over addition. So m times n plus p will equal m times n plus m times p. One is an integer and is the multiplicative identity. And if I multiply by 0, the product will be 0. And folks, knowing those rules for operations with signed numbers, as well as, knowing the properties and being able to show the rules, how they work with counters and number lines and mail time stories is what I expect of you from chapter 5. Your the homework for chapter 5 involves all of that. Do you folks have any questions at all about the sign numbers, about using the counters and using the number lines to show those operations? I'm going to stop sharing for a minute so I can look at you. Any questions on any of that from chapter 5? Are we all good? You all feel you're such pros with your positive and negative numbers that if you had to go in front of a group of elementary students right now, you could explain it so well that they would never get them wrong. Yeah? Well, get yourselves there, folks. So then, if there are no other questions on what's in chapter 5, what I had thought that we would do for the rest of today is just a little bit of introduction, to chapter 6. And in terms of that introduction, to chapter 6. I had thought that we could look at those chapter 6 activities that I had put in Blackboard. Again, I think the numbering of the ooh, that's not the one I wanted. I think that the numbering of the activities is pretty much the same. And so activity 1 and activity 3, if I'm not mistaken, both deal with, actually, no, I take that back. Activity 1 deals with the definition of fractions. And so in order to do that first part, you're supposed to be using your pattern blocks. So I took the liberty today of Googling up virtual pattern shapes. And I got this. And so with the pattern blocks, when we talk about the yellow, whoops, let me try that again. I don't want to totally get rid of that screen. Maybe if I move this one over here and this one, oh, this one over here. When we talk about the yellow hexagon, we're talking about this shape. When we're talking about the red trapezoid, we're talking about this shape. The green triangle would be here. And the blue rhombus would be here. And so I do believe that all of these are available as hands-on manipulatives in the little Ziploc container in the back of your activity manual. So let's, question 1, compare the red trapezoid to the yellow hexagon. The red trapezoid would be what fraction of the yellow hexagon?
Yeah.
And why?
Those two trapezoids make one hexagon.
Okay, so are we all in agreement that since 2 trapezoids make 1 hexagon, the trapezoid would be half of the hexagon? So now I'm going to move my trapezoids out of the way. Could you folks play around with your blue rhombuses and figure out how many blue rhombuses would it take to cover that yellow hexagon? And so what fraction of the yellow hexagon is that blue rhombus? Any ideas?
1/3.
1/3. Why?
Because 3 of the rhombuses fit on the hexagon, on the
Beautiful.
hexagon.
I like it. So now how about the triangle? What fraction of the hexagon is that green triangle? As you play with your pattern blocks, how many triangles does it take to fill the hexagon?
6.
6. So the triangle would be what fraction of the hexagon?
1/6.
Beautiful. Now what we want to do is we want to compare the triangle to the blue rhombus. And so the triangle would be what fraction of the blue rhombus and why?
One half because two triangles fit on the rhombus.
Beautiful. And then lastly, the triangle would be what fraction of the trapezoid?
One third because three triangles fit on the trapezoid.
Beautiful. And sort of a fun way of looking at those fractions. Now, next part of the activity asks you what fraction of each figure is shaded and unshaded. So why doesn't everybody take a couple of minutes to look at that? And so in number one, what fraction would be shaded?
2/6.
Beautiful. And so what's unshaded?
4/6.
Beautiful. How about in number two? What do we have shaded?
4/7.
So unshaded is,
3/7.
how about number three?
1/4.
1/4 is unshaded, right?
Oh, yeah.
So yeah, so 3/4 is shaded. I knew what you meant. And then the last one?
Um, 3/5 shaded.
And 2/5 unshaded. So, and then the second page deals with something that's a little bit different. They're your Cuisenaire rods. And so you can, hopefully you cut them out. With the Cuisenaire rods, I don't think we've really discussed them yet. They're rods of different lengths, and each color represents a specific length between the numbers 1 and 10. And so I was able to find online a pretty neat set of virtual Cuisenaire rods. And so, oh, is this the set of them that I wanted? Let me, so that the number 1 is the white, then the number 2 are the, red, the number 3 are the green, the number 4 are the purple, the number 5 are the yellow, the number 6 are the darker green. Now I'm questioning myself. Is this color scheme coordinating with the ones that you guys have in your packet? Oh yeah. The numbers 7 are the black. The numbers 8 are the brown. 9 are the bright blue, and 10 are the orange. And so what the activity asks you to do is to decide by comparison. First activity says, so let's say that our orange represents our number 1. And if the orange represents the number 1, what, whoops, fraction would be the red, the yellow, the green, the purple, and so on. And so let's have you folks take a minute and use your own rods to answer this page from the activity manual. And why is this not letting me slide it around? So I'm going to be quiet and let you folks work on those for a minute. Celestina, I got that you're here. We're working in the activity manual, chapter 6. What? Can you folks hear me okay, or is it breaking up?
I could hear you.
Okay. So are we at a go over place or are we still working? So if the orange represents the number 1, what fraction would the red represent? And why? How many reds? I've got to figure out how to rotate these. How many reds would it take to, does anybody know how to rotate these guys? How many reds would it take to fill in the orange? Any ideas? What fraction would the red be of the orange?
I had 5.
So 5 reds make the orange. So could we say that the red is 1/5? And how about the yellow? How many yellows does it take to make the orange?
2.
2. So that would be
1/2.
1/2. All right, I'm trying, and this technology is failing me. I'm sorry. How about the green? What fraction of the orange would you say the green is?
I got 4.
I guess it depends which green we're looking at. I was looking at the dark green, but now I'm thinking that they might have been looking at the light green. And so if I look at that light green, 1, 2, 3 aren't going to do it, but 1's too much. How could we think of that light green as being a fraction of the orange? Any ideas? Could we think of it as 3/10? And in the same way, wouldn't the purple be 4/10? Yes? No, maybe? What do you think? So now if the purple rod represents 1, what would the brown rod be? Wouldn't that be twice as long, or the fraction 2/1? And if I were to look at the dark green as being a fraction of the purple, do you see how the dark green would be like 1.5 or 3/2 or 6/4? And if I were to compare the purple to the orange, that 2.5, or we could think of that as 5/2. And then how about if I were to compare the purple to the black? It's more than 1. Wouldn't it be 1 3/4 or 7/4? What are you folks thinking? And so now I have to apologize. I have all of these red ones going in the other direction. If the red rod is 1/2, which would be the whole, which would be 1? Any ideas? You folks are being awfully quiet. Purple, thank you. Instead, if the red is 1/3, which would be 1?
Dark green.
Beautiful. What about if the white one were 1/5? Which color would be the whole?
Is it the dark green again?
Well, let's see. How many white ones would it take us to fill in the dark green? If the white one has a length of 1 and the dark green has a length of 6, I would think that that might be more than 1/5.
Oh, the yellow.
The yellow, yeah, I'm thinking the yellow. Anybody else in agreement with the yellow? And so now if the white is 1/4, which one would be 1 3/4? So if the white is 1/4, I'm assuming that the purple will be 1. And so then if I add 3 more quarters, wouldn't that take me to the black? And so if the red is a half, 1.5, and in an ideal world, I was going to be able to get some more reds oriented that way. I don't know why it's not liking me. I played with this all afternoon and it seemed to work. Well, if the red is a half, 2 reds would be a whole. And then if I add another red, wouldn't that take me to the 6, which is the dark green? And then if the red is a third, well then, let's see, 3 reds would give me 6, which is a whole. And then adding 2/3 on top of that whole, 1, 2, wouldn't that take us to the orange? Yes, no, maybe. And then that last part, they want us to make a shape like this out of 2 trapezoids. So 1 trapezoid, 2 trapezoids, and a blue rhombus. And so that shape represents my number 1. And so if the area of that shape is 1, what shape would have an area of a quarter? What shape would have an area, this guy over here too, of a half? What shape would have an area of an eighth? So are we getting any answers here? If this general shape is my basic unit, my 1, is there a shape that would be an 8? Is there a shape that I could fill this area in using 8 of the same shape? I'm working backwards, folks. Did anybody else get that they could fill in that basic shape with 8 triangles? So an 8th would be 1 triangle. And so if an 8th is 1 triangle, if it takes 8 triangles to fill that in, wouldn't I be able to, I'd have to arrange them carefully, but wouldn't I be able to fill that shape in with 4 of the blue rhombuses? 1, 2, 3, 4. And so wouldn't a blue rhombus be a quarter? And so then let me put this back so I have the whole original thing. So what would be a half of that?
Two blue rhombus.
So, yep, we could have 2 blue rhombuses. Can anybody think of something else that would be a half?
Four triangles.
Beautiful, 4 triangles. And so now we're going to go back to that original shape. I'm going to pull everything else off of it. I made a mess of it. That was our original shape. They want us to fill in that same shape using 1 trapezoid, 2 blue rhombuses. So I'm going to have to take another rhombus and put it in there. And 1 triangle. And so a blue rhombus, I think we already said, was going to be 1/4. A green triangle, I think we already said, was going to be 1/8. But what would you say the fraction is for that red trapezoid? the red trapezoid, what fraction of the whole would that be? Any ideas? I'm waiting. Ah. What fraction would that be of this entire shape?
Would be
1/3?
1/4.
Let's see. Somebody just said something and I have to apologize that I didn't hear. I'm thinking we showed that it could be 4 rhombuses, so the rhombus is a 4th. We showed that it could be 8 triangles, so a triangle is an 1/8. The trapezoid is a little bit smaller than a half, because the whole thing is 2 trapezoids. Could we, let's see, I think at the beginning we said that a trapezoid was equal to 3 triangles. And so couldn't we say that that red trapezoid would be like the fraction 3/8? Does that make sense? And does it make sense in terms of comparing the areas of the shapes and the lengths of the rods, that we could use those concepts to look at the definition of a fraction, the meaning of a fraction? It being 1 of 3 equal parts would be a third, and so on. If that one's all right, I'm going to be quiet for a few minutes. Actually, do you folks all have your activity manuals with you? Yes? So rather than having everybody work alone, let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 people. Let's have the Zoom move you folks into, let's make 4 rooms. And so you'll be working in groups of 3 or 4. And I'm going to give you probably about 15 minutes to work on activity 3 together with the people in your group. Would you guys be more likely to talk if you were only talking to 2 or 3 other people in a group, as opposed to as a class as a whole? Because I really like to have the activities where you work together on hands-on things. So I'm going to create rooms, Zoom is gonna automatically assign you, so you're gonna be randomly assigned into a room with other folks. And I'm going to probably give you 5 minutes to work alone, and then I'm gonna start checking in on the different rooms and see how you're doing, okay? So, here you go. I think you folks, what do you have to do to join a room? You guys going into your, joining your rooms, is there something that popped up that you can? Leanne, are you there? Stephanie, were you not put in a group?
Can you hear me?
Yep, I can hear you. Can you hear me?
Okay, I was having difficulties logging in the beginning. And
Okay.
my phone is on 1%, so I was just coming back using this.
Okay, what we're doing is we're working on from chapter 6, activity 3 on equivalent fractions. It's in your activity manual on page 96. And it works with the relationship between some of our pattern blocks and our Cuisinart odds. And so everybody's been working diligently on them. Hopefully people are coming in from their breakout rooms and we're going to go over. So hopefully we didn't lose anybody in the process. Breakout room 2. It hasn't come back yet.
Yeah.
Hopefully, yep, here they are.
I need your keys.
They're on there somewhere.
Okay, so first question, how did that go? Is working together in breakout rooms something that you would like to do again in class or not?
Yes.
Yes? Okay.
Yes.
All right, we'll try to kind of work in the remaining activities that way. I know next class we'll be working on more of the other 2 ones of these chapter 6 activities. I know that I found out that a couple people didn't get an activity manual, that they weren't available when they went to buy them. All of the activities for each of the chapters that we've done are in an activity folder in the content section of Blackboard. And the cutouts for today, there are copies that you can print out and cut out for your manipulatives, also in the activities for chapter 6 folder. But should I share my screen so we can go over them together? And so I am an epic failure at working with those virtual rods. I can't get them to rotate and stand up straight. And so I'm going to just write on this picture here. They had asked us to do is stack them. And so this bottom one is the dark green. And then these 2 others should be your light green. And then these should be your red. And these should be your white. Well, I'm just going to put W's in for white because I can't write that neatly. So did everybody get it? Took 2 light greens to make a dark green. And so the light green is a half, or we could look at that as 3 out of the 6. It took 3 red to make a dark green. So that's a third, which gave me 2 out of the 6. The dark green was the whole, so that's 6 out of 6, or we could say 1 out of 1, or we could say 3 out of 3, or all of the different representations. Now that purple, that was the weird one. And so I'm going to be childish and play with my highlighters. The purple was equivalent to the length of 4. And so the purple, if I stood it on top, the purple would have been equivalent to 2 of the reds. So it would be 2/3. Or if we look at it as being 4 units, it would be 4 out of the 6. And could you see lining these strips up to show that a red is 1/3 of the dark green, or 2/6, or so on, to show those equivalent fraction relationships? So then the next one, what we've got is the brown is on the bottom. And then these two would be your purple. These, to line up to look like that, would have been our red. And then the single units are our white. And so the purple, if the brown is 1, the purple would be equivalent to 1 of 2 equal. Wouldn't it also be equivalent to 2 out of 4? And wouldn't it also be equivalent to 4 out of 8? Going to skip down to the red. It would take 4 red to make my brown. And so wouldn't each red be 1/4? Or if I combined it to that upper row with the whites, wouldn't it be 2 of 8? And so then I think this green pen is going to be the closest I get to dark green. The dark green has a length of 6. And so if I were to superimpose a dark green over this, wouldn't the dark green be like 3 of the 4ths, or also equivalent to 6/8? Yes, no, maybe. Okay, great. Then the next page asked us to make this star shape out of our pattern blocks. And now if I look at my pattern blocks, does everybody see that the star shape could be a hexagon with the little triangles? Or couldn't the star shape also be made out of 12 triangles? And now I want to compare it to the trapezoid. Well, the red trapezoid, we said that the red trapezoid is like a half a hexagon, or like 3 triangles. And so wouldn't that be 3/12? Or a quarter of my star? Now, if I look at a single blue rhombus is like 2 of the triangles, but I don't want a single blue rhombus. I want 2 of them. And so let's see. If I look at those 2 blue rhombuses, well, wouldn't it take a total of 6 of them to fill in the whole gosh darn star shape? And so wouldn't that be 2/6? Or wouldn't I have 1/3 filled in? Or if I look at it in terms of all of those little triangles, wouldn't that be 4 out of the 12 triangles? So far, so good? And then instead, if I look at the hexagon, the basic hexagon, that yellow hexagon, is this part. And isn't that yellow hexagon made up of 6 of the 12 triangles? Or wouldn't it be made out of 3 of the 6 rhombuses? Or wouldn't it be half of the whole? Okie dokie. And then this last part asks you to work with the fraction strips. And that's what I'd like to end with today, is looking at those fraction strips to give a physical comparison of the different equivalent fractions, which we'll more rigorously define next week. And in order to do that, I have to move you folks. And yes, I did include a page of the fraction strips with today's notes. And oh, I'm sorry, I hate getting rid of you guys, but sometimes I'm not real good at manipulating the technology. And so if I look at these fraction strips, if we were on campus, I do have in my office a tote full of fraction trays, where it's a great big tray and there's one that would be equivalent to length 1 that fills it in. There are 2 halves that would be equivalent to the 1, and so on. And so when they ask you to write the name of equivalent fractions in the space provided, and I'm looking for fractions equivalent to a half, the way in which I would look at it is I would say, all right, this is a half. And so if I go through and I look straight down to see what meets up exactly with a half, we've got a half. And does everybody see that using the length of a half, it would be equivalent to the length of 2/4. Likewise, falling right here, wouldn't it be equivalent to the length of 3/6? In the same way, wouldn't this line be equivalent to the length of 1, 2, 3, 4/8? Wouldn't it be equivalent to the length of 1, 2, 3, 4, 5/12? I'm sorry, 5/10. I apologize. And also equivalent to the length of 6/12. And so can everybody see by the way those strips line up that 1/2 is the same as 2/4, 3/6, 4/8, 5/10, or 6/12? I'm sorry. I wish I was good with technology. I wrote that, take that page and you wouldn't be tilting your heads. But does it make sense? And so I've scribbled all over this. I'm going to erase what I just scribbled. And so now in the same way, looking at these strips, the next question asks, what would be equivalent to 2/3? So 2/3 would be this line here. It would be these two put together. And so if I picture folding there, wouldn't that length of 2/3 doesn't line up with the quarters, doesn't line up with the fifths, but doesn't it line up with 4/6? Doesn't it line up with 1, 2, 3, 4, 5, 6/9? And doesn't it line up with 1, 2, 3, 4, 5, 6, 7, 8/12? And so by the fact that they all line up, couldn't I say that 2/3 is equivalent to 4/6, is equivalent to 6/9, is equivalent to 8/12? Because they all have the same length. And could you picture with children trying to line up these lengths to see which are equal, which are equivalent? And so the last activity asks us what would be equivalent. I guess I'll pull out my highlighter here to 3/4. And so let's see, no halves, no thirds, no fifths, no sixths, no sevenths. But wouldn't that have that same length as 1, 2, 3, 4, 5, 6/8? And also going across, let's see, it doesn't meet with the 9ths, the 10ths, the 11ths, but over here, doesn't it meet with, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9/12? And so do you see how lining these fraction strips up so that they meet and we can see which are equal lengths can give us an introduction to this idea of fractions having different looking names but being equal? Would that be a use of manipulatives that you think might give a little bit more meaning to that idea of equivalent fractions? Well, look at, they all have that same length to kind of describe that idea to children. Yes? And so, can you tell from what we've done with these activities that chapter 6 is going to take us? We started looking at problem solving. Then we started looking at our sets and in whole counting numbers. and cardinal numbers. Then we looked at the whole numbers in the operations. Then we added the signed numbers, the integers. And now we're going to expand our horizons to rational numbers or ratios or fractions. And so that's where we'll be going in chapter 6. Chapter 7 takes it a little bit further to the idea of decimals, which is one specific type of fraction. So chapter 6 and 7 will be that 4th unit that we look at. They'll be our test 4. So let me get rid of the breakout rooms. Let me stop sharing my screen. Let me ask, does these activities with manipulatives to introduce the idea of fractions being part of a whole and the equivalence of fractions, all right? And how are all of you with your signed numbers, your positive and negative numbers on a number line, working with those sets of red and black counters? Everybody all right with that? And you've all started working on that chapter 5 homework and nobody's got any questions yet?
Not yet.
Not yet. All right, well, if you do come up with questions on the chapter 5 homework, please send me an email or please stop by my office hours because I'm hoping that that bribe of 10 extra points, I'm keep crossing all my fingers and toes, is enough to incentivize you to get those chapter 5 homeworks done by Monday so that I can grade them Tuesday. And then I'll send you guys an email when they're all done in Blackboard and you can go back and look at them and see how you did. I know I did get an email from somebody with concerns about their chapter 4 homework. And if you ever have concerns with how I graded something, you should be able to access the graded paper through Blackboard. And if you're questioning how I graded something or what you did, why it was right, why it was wrong, please stop by my office hours or shoot me an email and I can either meet with you during office hours, communicate with you via email, or we can try to come up with a one-on-one Zoom, okay? Otherwise, I know we're a little bit early, about a half an hour early, because I think we're supposed to go until about 8:45. But because after 2.5 hours, every time I use this Surface today, it shut down because it overheated. I don't want to black out on you guys. And somehow we're about a week ahead of where I had thought we would be. And so is everybody all right if we call it a night? Any questions on anything? Anything I can do for anybody? Now, the superstitious old lady here is going to ask you folks to please, whatever you were doing last Sunday that helped make the Bills win by so much, repeat your behaviors. All right. And if there's ever anything that I can do for you, please never be embarrassed to reach out, to send an email, to ask a question, to come to the office hours. And I don't know, how big a bribe do I have to make to get you folks to talk in class? Because by the end of the night, I have a sore throat because none of you are doing any of the talking. It hurts. I'm going to beat you up. So have a good evening, folks. Bye-bye.
Bye.
Bye.
Bye. Deanna?